What if everything you see around you, the chair you're sitting on, the stars in the night sky, even the air you're breathing, isn't as solid or as smooth as it seems? Beneath the surface of reality, at scales so tiny our finest instruments can barely glimpse them, the fabric of space and time itself might be churning like an endless ocean. This turbulent, frothy sea is what physicists call quantum foam, and it's one of the most astonishing and perplexing ideas in modern science. Picture the universe not as a calm, unbroken expanse, but as a bubbling cauldron of energy where particles wink in and out of existence in fractions of a second. Places where the rules of gravity and quantum mechanics collide, where the very idea of here and now might not even apply. And here's the wild part. We don't just suspect this foam exists. Some of the brightest minds in physics have spent decades trying to unravel its secrets, and what they've discovered will reshape how you think about reality itself. Today, we're diving headfirst into this cosmic mystery with 30 mind-bending theories about quantum foam. Some of these ideas will sound like science fiction wormholes hiding in the fabric of space, miniature black holes popping into existence and vanishing before we can detect them. Even the possibility that our entire universe is just one bubble in an infinite quantum froth. Others hint at something even stranger, that this foam might hold the key to unlocking time travel, dark energy, or the ultimate theory of everything. The deeper we go, the more questions we uncover. Could quantum foam explain why the universe is expanding faster than it should? Does it connect parallel dimensions we can't yet see? The answers might be hiding in the math, waiting for someone bold enough to piece them together. But here's what makes this journey so thrilling. Quantum foam isn't just a puzzle for physicists in lab coats. It's a frontier that challenges everything we think we know about existence. Every flicker of energy in that foam, every fleeting distortion of space, could be rewriting the rules right under our noses. And the most incredible part, you don't need a PhD to join the adventure. Today, we'll walk through these theories step by step, from the eerily plausible to the delightfully outlandish. By the time we're done, you'll see the universe and your place in it in a way you never have before. So buckle up, reality is about to get a lot more interesting. Imagine spacetime not as a blank, static stage where the universe unfolds, but as a living, breathing thing, twisting and bubbling beneath everything we see. This is the heart of our first theory, that quantum foam isn't just a curiosity lurking in the background of reality. It is reality. At scales a billion times smaller than an atom, the smooth fabric of space and time dissolves into a frenzied dance of energy. Particles and forces don't move across a steady surface. They surf waves of creation and destruction where empty space isn't empty at all. It's a seething ocean of potential where gravity and quantum mechanics meet in a battle we're only beginning to understand. Take gravity, for example. Einstein told us it's the curvature of space-time, but down in the quantum foam, that elegant bend might shatter into fragments. Picture a hillside covered in gravel. From far away, it looks like a smooth slope, but up close, it's jagged and unpredictable. That's space-time at the Planck scale. Particles don't glide effortlessly, they stumble through a storm. Some physicists think this could explain why gravity feels so weak compared to other forces. It's not that gravity is faint, it's just that most of its power gets lost in the chaos of the foam. And here's where things get even wilder. If space-time is truly this turbulent, it might rewrite how we think about particles themselves. Electrons, quarks, even light, what if they're not just objects moving through space, but ripples emerging from it? Think of the foam as a supercharged version of static on an old TV screen. Most of it cancels out, but sometimes patterns stabilize long enough to become the matter and energy we recognize. That means the chair you're sitting on right now might not be a solid thing at all, just a temporary knot in the froth of the universe. The most tantalizing clue: black holes. These cosmic vacuum cleaners don't just bend spacetime, they shred it. At their cores, where gravity becomes infinite, our current laws of physics break down. But what if that's not a flaw in the math? What if it's a glimpse of quantum foam in its rawest form? Some theories suggest black holes aren't just tearing space. They're churning it, turning the calm fabric we know into a boiling frenzy where time itself might loop or fracture. If that's true, then every black hole could be a window into the true, chaotic heart of reality. Yet for all its chaos, quantum foam might hold a bizarre kind of order. Just like foam on the ocean follows unseen currents, these spacetime fluctuations could secretly obey deeper rules we haven't discovered yet. Unlocking them wouldn't just solve puzzles like dark energy or the birth of the universe. It'd prove something profound, that even in the most turbulent corners of existence, there's a pattern waiting to be found. Now let's dive into something even more mind-bending. What if those quantum bubbles and fluctuations weren't just random chaos but tiny doorways? Imagine spacetime isn't just frothy but riddled with microscopic tunnels threading through the universe like hidden passageways. This is theory 2, wormholes lurking in the quantum foam, so small we'd need a microscope 1,000,000,000 times more powerful than anything we've built just to glimpse them. But their size doesn't diminish their potential. If they exist, these wormholes could be stitching the cosmos together in ways we're only beginning to fathom. Think of space like a sheet of paper. Normally, to get from one side to the other, you'd have to travel the full distance. But what if you could fold that paper, poking a tiny hole through it? That's the essence of a wormhole, a shortcut through spacetime. Most people picture them as giant, stable tunnels for spaceships, but the quantum foam version would be far stranger. These wouldn't be cosmic highways, they'd be fleeting, subatomic threads, flickering in and out of existence so fast you'd need a stopwatch measuring in quintillionths of a second to catch them. So why does this matter? Because even if they're vanishingly small and brief, their effects could be profound. Some physicists speculate that these micro-wormholes might act like quantum teleporters, instantly linking particles across vast distances. Under the right conditions, a bit of information or even an atom's worth of energy could hop from one side of the universe to the other without ever crossing the space in between. It sounds like magic, but it's rooted in the math of quantum mechanics. In fact, some theories suggest this could explain the bizarre phenomenon of quantum entanglement, where particles influence each other instantly, no matter how far apart they are. But here's where it gets really wild. If these wormholes aren't just shortcuts through our universe, but bridges to entirely other ones, the implications are staggering. The foam might not just connect different places, it could connect different realities. Imagine a froth of spacetime bubbles, each one its own universe with its own laws, and these wormholes threading them together like stitches in a vast cosmic quilt. Suddenly, the multiverse isn't just a speculative idea, it's woven into the fabric of reality itself. Of course, there's a catch. Wormholes, even microscopic ones, are notoriously unstable. According to Einstein's equations, they'd snap shut almost instantly unless held open by something exotic, like negative energy or matter with repulsive gravity. And that's the puzzle. Does the quantum foam naturally generate conditions where wormholes could stay open, even briefly? Some models say yes, hinting that the foam's turbulence might provide just enough energy to keep these tunnels intact long enough for particles to slip through. It's a long shot, but if true, it would mean the universe is far more interconnected than we ever dreamed. The real kicker: we might already have clues. Black holes, those space-time warping monsters, could be tangled up in this wormhole mystery. Some theories suggest that what we call a black hole's singularity, the point of infinite density at its core, might actually be a wormhole's mouth leading somewhere else entirely. Even stranger, the Hawking radiation leaking from black holes might carry traces of these hidden tunnels, like echoes from another side of reality. So while we can't zoom in on quantum foam with today's tech, the search isn't hopeless. Future experiments with ultra-sensitive gravity waves detectors or quantum computers might catch whispers of these wormholes, tiny ripples in the fabric of spacetime betraying their presence. And if we do, it wouldn't just revolutionize physics. It'd redefine what's possible, turning science fiction staples like instant travel or parallel universes into the next great frontier of human exploration. For now, these wormholes remain ghosts in the math, but the mere possibility reminds us that the quantum foam isn't just a scientific curiosity. It could be the universe's best-kept secret waiting to rewrite the rules. But what if the quantum foam isn't just reshaping our understanding of space and time, but fueling the universe itself? This brings us to Theory 3, one of the most provocative ideas in modern cosmology. That dark energy, the invisible force ripping the cosmos apart at ever-increasing speeds, might be bubbling up from the quantum foam. Picture this: every tiny fluctuation in that frothy spacetime sea isn't just random noise, it's energy. And when you add up all those microscopic ripples across the vastness of the universe, they might be pushing galaxies apart in a way that's baffled scientists for decades. Dark energy is one of the biggest mysteries in physics. We know it exists because the universe isn't just expanding, it's accelerating, as if some unseen hand is stretching the fabric of reality faster and faster. But what is it? One leading idea is that the quantum foam's ceaseless churn generates a kind of background energy so pervasive, it acts like anti-gravity on cosmic scales. Think of it like static electricity, but for spacetime itself. Even in a perfect vacuum where classical physics says there should be nothing, the foam ensures space is never truly empty. It's a sea of virtual particles popping in and out of existence, each borrowing energy from the universe for the briefest moment. And some theories suggest that borrowed energy might not fully cancel out. Over unimaginable distances, those tiny leftovers could add up to the dark energy we observe. Here's the twist: if this is true, it would solve one puzzle while creating another. Quantum field theory predicts the energy density of the foam should be enormous, roughly 1 followed by 120 zeros times stronger than what we measure for dark energy. That's like predicting a tsunami and finding only a ripple. Physicists call this the cosmological constant problem, and it's been a thorn in their side for generations. Some suggest the foam's energy might cancel out in ways we don't yet understand, leaving just a faint residue behind, the dark energy we see. Others propose even wilder fixes, like extra dimensions siphoning off most of that energy into hidden realms. But let's step back and ask, what does this mean for the fate of the universe? If dark energy truly stems from quantum foam, its behavior isn't just a curiosity, it's a countdown clock. Right now, the acceleration is gentle enough that galaxies outside our local group will simply vanish into the distance over trillions of years. But if the foam's energy density isn't perfectly constant, if it changes over time, the future could be far more dramatic. Some models suggest dark energy might grow stronger, eventually tearing apart galaxies, stars, and even atoms in a catastrophic big rip. Others imagine it fading away, allowing gravity to pull the cosmos back into a fiery collapse. The stakes couldn't be higher. If the foam is the source, then understanding its structure isn't just about subatomic physics. It's about reading the universe's expiration date. And here's the kicker: we might already have clues buried in the cosmos. Tiny irregularities in the cosmic microwave background, the afterglow of the Big Bang, could hold fingerprints of the foam's influence. Future telescopes, like the European Space Agency's Euclid mission, are hunting for these signatures right now. So while quantum foam might seem like an abstract curiosity, it's playing for keeps. Its ripples could be the hidden engine behind the cosmos's greatest mystery, and the key to whether our universe ends with a bang, a whisper, or something stranger than we've dared to imagine. Now consider this: what if everything you perceive as three-dimensional reality is actually a grand illusion, like a cosmic mirage? This is the heart of Theory 4, where quantum foam collides with one of the most radical ideas in physics, the holographic principle. Imagine the universe isn't built like a solid block, but more like a movie projected onto a screen. Every star, every galaxy, even your own thoughts might just be shadows cast by information etched onto a two-dimensional surface at the edge of reality. And here's the kicker: quantum foam could be the static fizzing at the edges of that projection, the artifact revealing the true nature of existence. The holographic principle suggests that all the information making up our three-dimensional world, every particle interaction, every gravitational tug, is actually encoded on a distant two-dimensional boundary. It's like taking a black hole's event horizon and realizing everything that falls in leaves a perfect imprint on its surface. Stretch that idea to the entire cosmos, and suddenly, the quantum foam's chaos starts to make eerie sense. Those frothy fluctuations might not be random noise, they could be the pixelation of reality itself, the graininess of a universe rendered in finite detail. Think of it like a hologram on your credit card. Tilt it, and the flat surface produces a stunning 3D image, but zoom in close enough, and you'll see the tiny dots that make up the illusion. Quantum foam could be those dots for the universe, evidence that what we call space is just a dense network of information. This turns classical physics on its head. Instead of empty void between stars, there's a buzzing hive of data, where even the tiniest volume of space holds an unimaginable amount of encoded information. But how does this connect to quantum foam? Because at the Planck scale, spacetime's turbulence might not be chaos, it could be computation. Picture the foam as a cosmic processor, constantly recalculating reality. Each bubble isn't just energy, it's a bit in the universe's hard drive, flickering between states to maintain the illusion of continuity. This explains why particles can be in two places at once until observed. The system hasn't finished rendering the answer yet. The implications are staggering. If the holographic principle is true, then black holes aren't just cosmic trash compactors, they're the universe's archival system. When matter falls in, its information isn't destroyed, it's smeared onto the surface like ink on parchment. And quantum foam, that's the universe's way of defragging its memory, shuffling bits to keep the cosmic simulation running smoothly. Critics argue this sounds more like philosophy than physics, but the math backs it up. Equations describing black holes show their surface area, not volume, determines their entropy, a clue that information lives on the boundary. And experiments with gravity wave detectors have hunted for hints of this pixelation in spacetime itself. While we haven't found smoking gun evidence yet, the search is rewriting how we see reality. Here's the wildest twist: if the holographic principle holds, then free will might be part of the illusion. Your choices could feel real, but they'd be as predetermined as pixels in a movie. Or perhaps consciousness itself is part of the code, a feedback loop between the projection and the surface. Suddenly, quantum foam isn't just about physics, it's about the nature of existence. Whether the universe is truly a hologram remains an open question, but the mere possibility forces us to confront a profound truth. Reality might be far stranger, far more intricate than we ever dared to dream. And the answers could be hiding in the foam's flickering code, waiting to be deciphered. Time isn't the steady, unbroken river we experience. What if it's more like froth on a cappuccino, bubbling into existence moment by moment? This is Theory 5, where quantum foam doesn't just warp space, it might create time itself. Imagine the universe's clock isn't ticking smoothly but stuttering, with every instant emerging from the foam's chaotic dance. At the Planck scale, where spacetime dissolves into turbulence, the distinction between before and after could blur into meaninglessness. Time might not flow, it could flicker, stitched together by quantum fluctuations like a cosmic flipbook. Physicists have long struggled to explain why time moves forward at all. The laws of physics work just as well in reverse, yet eggs don't unscramble and memories only point to the past. This arrow of time has been pinned to entropy, the universe's tendency toward disorder. But quantum foam offers a wilder possibility that time's flow isn't fundamental. It's an illusion emerging from the foam's probabilistic nature. Think of it like watching rain fall on a pond. From a distance, you see smooth ripples expanding outward, the arrow of time. But up close, each drop strikes randomly with no inherent direction. The foam could be those droplets and time the ripple we mistake for reality. Here's where causality gets turned on its head. If time is stitched together by quantum events, then cause and effect might not be set in stone. At microscopic scales, particles routinely defy classical logic, existing in multiple states until observed. Apply that to time, and you get scenarios where the future could influence the past, or where events unfold in loops rather than lines. Picture a universe where every decision branches into possibilities, and the foam's fluctuations collapse not just where something happens, but when. The math even hints at something stranger. In certain quantum gravity models, spacetime's foam-like structure allows for tiny, closed loops in time like microscopic time machines. These wouldn't let you revisit yesterday, but they might permit particles to briefly interact with their own past. Some theorists suggest this could explain quantum entanglement's spooky action at a distance. Particles aren't communicating faster than light. They're just threaded through time in ways we can't yet map. But the real bombshell, if time emerges from the foam, it might not exist at the deepest level of reality. The universe's fundamental code could be timeless, with time as a user interface our brain's construct to navigate the chaos. Like a computer rendering a 3D game frame by frame, the foam's fluctuations could generate the illusion of continuity. This would mean the Big Bang wasn't just the start of matter and energy, it was the moment time itself crystallized from the froth. Experiments are already hunting for clues. Ultra-precise atomic clocks have detected subtle inconsistencies in time's passage, as if it shimmers at tiny scales. Others are probing quantum systems for evidence of retrocausality effects that precede their causes. If either bears fruit, we'll have to rewrite not just physics textbooks, but our very understanding of history, memory, and free will. After all, how can you change the future if the future is already whispering to the past? The beauty of this idea lies in its humility. Time, the scaffold of our existence, might just be a side effect, a glitch in the foam's infinite computation. And if that's true, then every tick of the clock is a miracle. A fleeting order snatched from chaos, a heartbeat echoing across the quantum void. Black holes aren't just cosmic vacuum cleaners, they're also the universe's most efficient shredders of information. Toss a book into one, and according to classical physics, every word, every letter, even the ink's chemical structure is lost forever, crushed into the singularity's infinite density. But Stephen Hawking threw a wrench into that idea when he discovered black holes aren't truly black, they glow, they radiate, they slowly evaporate. And that glow, now called Hawking radiation, carries a devastating implication. If the black hole vanishes, what happens to all that swallowed information? This is the infamous black hole information paradox, and quantum foam might hold the key to solving it. Here's the puzzle in a nutshell. Quantum mechanics insists information can never be destroyed. It can change form, but it must persist. Yet black holes, by their very nature, seem to violate this rule. Hawking's calculations suggested the radiation leaking from them was purely thermal, random noise with no trace of the original objects that fell in. That would mean the universe has a permanent amnesia problem, erasing its own history. For decades, physicists wrestled with this contradiction until an audacious idea emerged. What if the information isn't lost at all, but preserved in the quantum foam flickering at the black hole's surface? Think of a black hole's event horizon not as a smooth, one-way membrane, but as a seething layer of quantum foam. Every particle that crosses it doesn't just vanish. It leaves an imprint in that froth, like a fingerprint pressed into wet sand. This is the essence of the holographic principle we touched on earlier, but with a twist specific to black holes. The foam's chaotic fluctuations could encode the infalling matter's information in microscopic ripples, storing it in a scrambled, nearly indecipherable form. Hawking radiation, then, wouldn't be random, it'd be subtly modulated by those imprints, like a radio signal carrying encrypted data. Over trillions of years, as the black hole evaporates, every bit of information might eventually leak back out, hidden in the radiation's quantum noise. But how does this solve the paradox? Because if the foam at the horizon preserves information, then nothing truly disappears. It just transforms. Imagine shredding a confidential document. If you keep every single scrap, in theory, you could reconstruct the original. Quantum foam might be nature's version of that meticulous filing system, ensuring no cosmic document is ever truly destroyed. The math behind this is staggering. It suggests the surface area of a black hole's horizon, not its volume, determines how much information it can hold. That's why a black hole's entropy, a measure of its hidden information, is proportional to its surface area, a clue that the real action happens in the foam's two-dimensional dance. Of course, there are skeptics. Some argue this shifts the problem rather than solving it. How exactly does the foam encode complex information like the spin of an electron or the charge of a proton? Others propose even wilder ideas, like black holes birthing baby universes where the information escapes, rendering our paradox moot. But the foam-centric view has one compelling advantage. It fits with the broader puzzle of quantum gravity. If spacetime itself is inherently frothy, then black holes aren't exceptions, they're magnifying glasses, revealing the foam's role in stitching reality together. The implications ripple far beyond black holes. If quantum foam can preserve information against infinite gravity, it might rewrite how we think about the Big Bang's singularity or the fate of information in a hypothetical Big Crunch. Even more tantalizing, it hints that foam-like structure could be universal, not just at black hole horizons, but woven through all of spacetime. Future gravity wave detectors or quantum computers might one day probe these ideas, searching for the foam's footprint in the faintest echoes of colliding black holes. For now, the paradox isn't fully resolved, but the mere possibility that quantum foam could bridge the gap between gravity and quantum mechanics, between destruction and preservation, shows just how profound its turbulence might be. Black holes aren't cosmic dead ends. They could be the universe's most sophisticated storage devices, their secrets etched in foam at the edge of oblivion. What if the universe isn't just governed by physical laws, but is running them like software on some unimaginable cosmic machine? This is the bold claim of Theory 7. That quantum foam isn't just a backdrop for reality, but the universe's operating system, crunching calculations at scales so small they make atoms look like planets. Imagine spacetime itself isn't passive, it's processing. Every fluctuation in the foam, every flicker of energy, could be part of an infinite computation, executing the code that makes stars burn, particles collide, and time move forward. The idea builds on a radical shift in physics. That information isn't just something the universe contains, it's something the universe is. At the quantum level, particles behave less like tiny billiard balls and more like bits in a cosmic processor, flipping between states to execute the program we call reality. The foam's turbulence might be the visual noise of this computation, the universe's way of juggling probabilities until they collapse into the world we see. Think of it like static on an old TV, seemingly random, but actually encoding the signal beneath. But how would this even work? Consider a quantum computer. Unlike classical computers with binary bits, zeros and ones, quantum bits, qubits, can exist in multiple states at once. This lets them perform calculations at dizzying speeds, solving problems in minutes that would take conventional machines millennia. Now scale that up to the Planck level, where spacetime itself is frothing with energy. If each bubble in the foam acts like a qubit, the universe isn't just using quantum computation, it is processing the cosmic source code in real time. Some physicists take this further, suggesting the foam's computations might explain why quantum particles behave so bizarrely. Take superposition, where particles exist in multiple states until measured. In a computational universe, this isn't a paradox, it's just the system holding multiple possible outcomes in memory until the result is needed. Even entanglement, where particles instantly influence each other across vast distances, could simply be 2 bits in the cosmic processor exchanging data faster than the speed of light because they're not really separated at all in the code. The strangest implication: if the foam is computing reality, then the laws of physics might not be fixed. They could be emergent, evolving algorithms fine-tuned over billions of years. This could explain why the universe seems so finely balanced for life, not because of a cosmic designer, but because the system has been running endless iterations, selecting for stability. It's like a video game engine optimizing itself frame by frame until the physics feels seamless. Critics ask who or what is running the program, but computationalists argue that's the wrong question. The universe might not need an external programmer. It could be self-sustaining, with the foam's fluctuations generating both the hardware and the software. After all, if spacetime and energy are just different expressions of information, then computation isn't something happening inside the universe, it's the universe's fundamental nature. Here's where it gets mind-blowing. If the cosmos is truly computational, we might one day find glitches in the matrix, tiny errors in the foam's calculations betraying the code beneath. Some scientists are already hunting for these anomalies, like subtle variations in the speed of light or gaps in quantum probabilities. Others suggest dark energy could be a background process, the universe allocating resources to keep the simulation running smoothly. Whether this theory holds up or not, it forces a profound shift in perspective. Reality might not be a stage, it's a story the universe is telling itself, written in the quantum foam's flickering logic. And if that's true, then every law of physics, every star in the sky, even your thoughts right now, are just data in the grandest computer of all. If empty space isn't truly empty, what's really going on in the quantum foam? Meet virtual particles, the universe's most elusive ghosts. These aren't just theoretical curiosities, they're fleeting bursts of matter and antimatter that pop into existence from the foam's raw energy, only to annihilate each other almost instantly. Picture a stormy ocean where droplets constantly leap from the waves before falling back, except here, the droplets are entire particles and the ocean is spacetime itself. The foam's turbulence doesn't just distort reality, it fuels it, lending energy to these temporary creations in a cosmic balancing act that defies common sense. Take the Casimir effect, one of virtual particles' most jaw-dropping signatures. Place 2 uncharged metal plates extremely close together in a vacuum, and they'll inexplicably pull toward each other. Classical physics says nothing should happen, but quantum foam tells a different story. Between the plates, only certain wavelengths of virtual particles can fit, while outside, all wavelengths surge freely. This imbalance creates a pressure differential, literally pushing the plates together. It's like sliding 2 combs into a turbulent river. The water's chaos outside exerts more force than the comma space between the teeth, forcing them to snap shut. This isn't just a lab trick, it's direct proof that the foam's energy is tangible enough to move objects. Then there's zero-point energy, the idea that even at absolute zero, when all classical motion stops, space still buzzes with quantum activity. The foam ensures there's no such thing as perfect stillness. Virtual particles flicker everywhere, their combined energy forming a baseline hum to the universe. Some theorists believe this energy could be harnessed. Imagine spacecraft tapping into the vacuum itself for propulsion, but the challenges are staggering. Most virtual particle pairs vanish in fractions of a nanosecond, and extracting usable energy from them would require manipulating spacetime on scales we can barely fathom. Experiments are inching closer to validating these ideas. Quantum squeezed light experiments manipulate vacuum fluctuations to reduce noise in particle detectors, essentially quieting the foam's randomness at specific frequencies. Others use ultra-cold atoms to simulate how virtual particles might behave near black hole horizons, where the foam's energy becomes extreme, the most tantalizing. Hypothetical UNRRA detectors, which, if built, could prove that an accelerating observer sees virtual particles as real radiation, a literal glow from the foam's churn. Yet the wildest implication isn't technical, it's philosophical. If virtual particles constantly borrow energy from the foam, then existence itself might be a cosmic mirage. Every atom in your body, every photon from a distant star, could owe its stability to a deeper chaos, a seething ocean where reality is forever borrowing, repaying, and redefining what real even means. What if every bubble in the quantum foam isn't just a fleeting ripple in our universe, but the seed of an entirely new one? This is where Theory 9 takes us into staggering territory, linking the froth of spacetime to the multiverse, a cosmic kaleidoscope where infinite realities bloom and fade. Imagine the foam's turbulence doesn't just distort space and time. It spawns whole universes, each with its own unique physics, its own version of stars, planets, even life. Some might have gravity 1,000 times stronger, others no gravity at all. Some could be so alien, matter itself behaves differently, and the wildest part. This isn't pure speculation. The math suggests it's possible. The idea hinges on a process called vacuum decay. Picture the quantum foam as a simmering pot of water, with each bubble representing a tiny region where spacetime's energy state fluctuates. Most of these bubbles pop harmlessly, but under the right conditions, say, a fluctuation with enough energy, a bubble might stabilize, expanding at the speed of light. Inside, the laws of physics could freeze into a new configuration distinct from our own. It's like blowing soap bubbles, but instead of soapy film, each one carries a self-contained cosmos with rewritten rules. This isn't just theoretical poetry. Inflationary cosmology, our best model for the Big Bang, suggests our entire universe might have begun this way, as a quantum bubble in some larger, foamy meta-reality. If that's true, then the multiverse isn't a distant hypothetical. It's happening right now, in dimensions we can't perceive. Some theorists even propose that black holes could be cosmic birthing chambers, their singularities punching through spacetime to create new universes in their wake. Every time a star collapses, every time particles collide at unimaginable energies, the foam might be knitting new realities into existence, but how would we ever prove it? One clue lies in the cosmic microwave background, the afterglow of the Big Bang. Strange anomalies in its pattern, like cold spots or uneven distributions, could be scars from collisions with other universes in the foam. Others suggest that gravity might leak between these sibling universes, creating subtle tugs on matter we can't otherwise explain. Future telescopes and particle accelerators might one day catch whispers of these interactions, turning multiverse theory from philosophy into hard science. The philosophical implications are just as dizzying. If an infinity of universes exists, then every possible version of you, every choice you didn't make, every chance you missed, might be playing out somewhere in the foam. But here's the twist: most of those universes would be inhospitable to life as we know it. The fact we exist in one where physics allows stars, planets, and consciousness might not be luck. It could be selection bias. We're here because only a universe this precise could produce observers to ask the question. Yet the multiverse idea isn't without controversy. Critics argue it's untestable, more metaphysics than physics. Others worry it renders science pointless. If every possible outcome happens somewhere, how do we distinguish laws from accidents? But supporters counter that the foam's structure offers a solution. If universes form along certain quantum pathways, there might be patterns in the chaos, a hidden family tree of cosmoses with shared traits. Finding those patterns could turn the multiverse from a provocative thought experiment into a predictive framework. For now, the multiverse remains a frontier. But the mere possibility reshapes how we see reality. The quantum foam isn't just the universe's fabric. It could be its loom, weaving endless variations into existence. And if that's true, then every time you glance at the night sky, you're not just looking at stars. You're glimpsing one thread in an infinite tapestry, where every flicker in the foam whispers of worlds beyond imagining. Gravity is the universe's architect, sculpting galaxies and bending light, yet at the quantum scale, it vanishes into the background like a ghost. This baffling disconnect is physics' greatest unsolved puzzle. Why does Einstein's elegant spacetime curvature refuse to play nice with the frenzied rules of quantum mechanics? Theory 10 suggests the answer is hiding in the quantum foam's chaotic swirl, where gravity might finally reveal its granular, quantized nature. Imagine if gravity isn't a smooth force at all, but emerges from countless tiny packets of energy flickering in the foam, like pixels composing an image so fine we've mistaken it for a continuous whole. For decades, physicists have chased this unification, searching for gravitons, the hypothetical particles thought to carry gravity's quantum signature. But here's the catch: gravitons, if they exist, would be absurdly weak. A single proton's gravity is about 40 orders of magnitude feebler than its electromagnetic pull, making gravitons nearly impossible to detect. Quantum foam offers a way out of this dead end. Instead of hunting solitary particles, we might need to study the foam's collective behavior, where spacetime's turbulence amplifies gravity's faintest whispers. Picture trying to hear a flute in a hurricane. Isolating one note is hopeless, but analyzing the storm's entire symphony could reveal hidden patterns. The math hints at something extraordinary. In some loop quantum gravity models, spacetime isn't infinitely divisible. It's woven from minuscule, indivisible atoms of space, each about 1 Planck length across. These wouldn't be particles floating in space, but the very fabric of space itself. Gravity, then, could arise from how these atoms interconnect, their quantum links stretching and warping like a cosmic mesh. When you stand on a scale, your weight might not come from some mysterious force, but from the sum of trillions of these microscopic spacetime interactions beneath your feet. But why does this matter beyond theoretical neatness? Because without quantized gravity, black holes remain paradoxes, the Big Bang an unsolvable mystery, and dark energy a frustrating enigma. Worse, our two foundational theories, general relativity and quantum mechanics, sit in incompatible kingdoms, each ruling their domain but refusing to speak the other's language. Quantum foam could be the translator, showing how gravity's smooth cosmic curves emerge from the frenetic jitter of the quantum world. Some of the sharpest clues come from black holes. When matter crosses their event horizons, quantum mechanics insists its information must persist, while relativity declares it's erased forever. The foam's structure might reconcile this by encoding information in spacetime's quantum links, like engraving data on the surface of a spinning top. Even Hawking radiation, the glow leaking from black holes, could carry imprints of the foam's gravitational pixels, offering experimentalists a path to test these ideas indirectly. The stakes couldn't be higher. If the foam truly quantizes gravity, it wouldn't just solve abstract puzzles, it'd revolutionize technology. Imagine materials engineered to manipulate spacetime's granular structure, or sensors detecting gravity waves with atomic precision. We might even crack time travel's code, harnessing the foam's fluctuations to bend time as easily as we bend light. Of course, skeptics argue we're chasing shadows. Without direct evidence, quantum gravity remains a beautiful hypothesis, but the foam's potential is too tantalizing to ignore. Future experiments like measuring spacetime's fuzziness with quantum-entangled particles or hunting for Planck-scale echoes in gravity wave data could turn speculation into fact. Until then, the foam whispers a promise that somewhere in its seething depths lies the key to gravity's final secret, waiting to unite the cosmos under a single, breathtaking rule. The universe is full of noise, cosmic static hissing from every corner of the sky, a cacophony of radio waves, gamma rays, and gravitational ripples all competing for our attention. But what if this noise isn't just random chaos? Theory 11 proposes something extraordinary, that quantum foam isn't merely a passive backdrop to the cosmos, but an active filter, subtly shaping the signals that reach us. Think of it like a cosmic colander, sifting out certain frequencies while letting others pass, quietly distorting the messages carried across the universe before they ever reach our telescopes. This idea flips how we interpret astrophysical data on its head. Take pulsars, those ultra-precise cosmic lighthouses whose radio pulses arrive with clockwork regularity. Occasionally, their signals show tiny, unexplainable hiccups, microscopic delays, or distortions. Most astronomers chalk this up to interstellar gas or dust, but some theorists suggest quantum foam could be the culprit. If spacetime at the smallest scales is truly frothy, then light traveling across billions of light-years wouldn't glide smoothly. It'd stumble through a maze of fluctuating bubbles, each subtly altering its path or energy. Over vast distances, those tiny deflections could add up like a whisper passed through a crowd, gradually garbled by countless interruptions. Even more intriguing is what this means for our search for extraterrestrial intelligence. SETI researchers spend decades scouring radio waves for patterned signals, but what if the foam is editing those messages before they arrive? A civilization broadcasting from a distant galaxy might send perfectly clear signals only for the quantum turbulence between us to scramble their transmissions into noise by the time they reach Earth. It's not that the cosmos is silent, we might just be listening through a sieve. Gravitational wave detectors like LIGO could hold the key to testing this. These instruments measure ripples in spacetime with absurd precision enough, perhaps, to detect the foam's granularity. If spacetime is pixelated at the Planck scale, then ultra-high-frequency gravitational waves might diffract as they pass through, like light bending through frosted glass. Future detectors, sensitive enough to catch these distortions, might finally glimpse the foam's signature in the warp and weft of spacetime itself. But here's the twist: if the foam does filter cosmic noise, it might also hide something profound. The universe's earliest moments, the first trillionth of a second after the Big Bang, should have generated gravitational waves at frequencies so high they'd be shredded by quantum turbulence before reaching us. That means the foam isn't just altering signals, it could be erasing entire chapters of cosmic history. The echoes of inflation, the birth cries of black holes, even clues to a pre-Big Bang universe, all might be lost in the static, drowned out by spacetime's own restless churn. Yet this filtering might not be a flaw in reality, it could be a feature. Just as Earth's atmosphere blocks harmful radiation while letting sunlight through, the foam's structure might shield us from cosmic chaos we're not equipped to handle. Certain high-energy particles or frequencies, if unfiltered, could destabilize matter or unravel quantum states. The foam, then, isn't just obscuring the universe's secrets, it might be protecting us from them. The implications stretch beyond astrophysics. If the foam filters information, then our entire perception of reality is already curated, like watching a movie through a fogged lens. What we call the universe might just be the fraction that makes it through the froth, a shadow of something far wilder, humming just beyond the edge of detection. Future telescopes, quantum sensors, or even experiments with entangled particles might one day peel back that veil. Until then, every signal from the cosmos comes with an unspoken asterisk, as interpreted by quantum foam. And that changes everything. What if the swirling chaos of quantum foam doesn't just shape the universe, but shapes you? Theory 12 plunges us into one of the most controversial ideas in modern science, that the froth of spacetime might be more than the backdrop to consciousness, it could be the canvas. Imagine your thoughts, your memories, even your sense of self aren't just electrical sparks in the brain, but ripples in the quantum foam itself. It's a notion that blurs the line between physics and philosophy, and it's backed by some of the boldest minds in the field. Take Sir Roger Penrose, the legendary physicist who helped unravel black holes. Alongside anesthesiologist Stuart Hameroff, he proposed that consciousness isn't purely biochemical, it's a quantum process. Their theory, dubbed orchestrated objective reduction or suggests that microtubules, tiny protein structures inside neurons, act as quantum computers, processing information via vibrations in the quantum foam. When these vibrations collapse, they don't just trigger neural firings, they generate moments of awareness. In this view, every time you make a decision or feel an emotion, you're not just running algorithms, you're surfing spacetime's turbulence. Critics pounce on this idea with valid concerns. The brain is warm, wet, and noisy, hardly the pristine lab environment needed to sustain delicate quantum states. Decoherence, the process where quantum systems get scrambled by their surroundings, should erase any quantum effects almost instantly. Yet Penrose and others counter that biological systems might exploit quantum biology, a field that's already found quantum effects in photosynthesis and bird migration. If nature can harness quantum weirdness elsewhere, why not in the brain? The implications are staggering. If consciousness taps into the foam, it might explain phenomena like intuition or creativity, moments when the brain seems to access information beyond classical computation. Some even speculate that near-death experiences, where people report vivid visions during clinical death, could be the foam's fluctuations persisting as brain activity shuts down. It's a radical departure from conventional neuroscience, but it offers something materialism often struggles with, a bridge between subjective experience and the physical world. Yet the skeptics aren't wrong to demand proof. So far, no experiment has definitively shown quantum processes in cognition, but the hunt is on. Some researchers are probing microtubules for quantum vibrations, while others simulate how quantum noise might influence decision-making. Even if arch or falters, the core idea that spacetime's structure and consciousness are intertwined refuses to die. After all, if the foam is the universe's most fundamental layer, shouldn't it leave fingerprints on everything, including the mind? Whether this theory holds or not, it forces a profound question. Are we bystanders in the universe or participants? If quantum foam feeds into consciousness, then observing the cosmos isn't a passive act, it's a collaboration, with the observer and the observed dancing in the froth together. And that changes not just how we see the brain, but how we see reality itself. Quantum foam isn't just a stage for the universe's smallest dramas. It might also be the reason we don't see quantum weirdness in our everyday lives. This is Theory 13, where we dive into one of quantum mechanics' greatest mysteries. Why do particles exist in multiple states at the subatomic level, yet everything we touch feels solid and predictable? The answer could lie in the chaotic churn of spacetime itself, where the foam's ceaseless turbulence forces quantum possibilities to collapse into single, classical outcomes. It's a phenomenon called decoherence, and it might finally explain why Schrödinger's cat isn't both alive and dead when you open the box, just one or the other. Think of quantum superpositions like a spinning coin. While it's in the air, it's neither fully heads nor tails, it's a blur of probabilities. But the moment it hits your palm, the spin collapses into a definite result. Decoherence suggests something similar happens in the quantum world, but instead of a hand stopping the coin, It's the relentless jostling of the foam that forces particles to pick a side. Every fluctuation in spacetime's fabric interacts with quantum systems, leaking information into the environment and destroying the delicate phase relationships that allow superpositions to exist. It's not that particles choose a state. It's that the universe's background noise drowns out their quantum ambiguity, leaving behind the crisp classical reality we recognize. This ties directly into the infamous measurement problem. Why does observing a quantum system seem to force it into a single state? Traditional interpretations, like the Copenhagen school, shrug and say observation defines reality. But decoherence offers a subtler answer. The foam doesn't care if a human is watching, it's always measuring everything all the time through its interactions. Your lab equipment, the air molecules bouncing around, even the cosmic microwave background radiation are all part of this relentless environment, constantly nudging quantum systems toward classical behavior. In this view, collapse isn't mystical, it's inevitable, driven by the universe's own restlessness. Some of the sharpest evidence comes from quantum computing. Qubits, the building blocks of these machines, lose their superposition states incredibly quickly unless shielded in ultra-cold, ultra-stable environments. The slightest vibration, temperature change, or stray electromagnetic field will decohere them, proof that even tiny interactions with the environment can destroy quantum magic. Now scale that up to the Planck level, where spacetime itself is vibrating, and you start to see why macroscopic objects don't quantum tunnel through walls or exist in two places at once. The foam's chaos is like a cosmic bulldozer, flattening quantum possibilities into classical certainties before they can scale up. But here's the twist: decoherence doesn't actually solve the measurement problem, it reframes it. If the foam is constantly collapsing superpositions, what decides which outcome manifests? This is where interpretations diverge. Some physicists argue the foam's randomness follows the probabilistic rules of quantum mechanics, while others propose hidden variables or even parallel universes branching off with each decoherence event. The wildest idea, that consciousness itself plays a role, with the foam acting as an intermediary between mind and matter, translating quantum potential into tangible experience. The implications stretch beyond theory. If we can model decoherence precisely, we might engineer systems to resist it, leading to quantum computers that don't need near absolute zero temperatures or error correction schemes chewing up processing power. Understanding the foam's role could also shed light on biological systems that seem to exploit quantum effects, like photosynthesis or avian navigation, where nature has somehow tamed decoherence to its advantage. Yet the deepest lesson lies in humility. Decoherence reminds us that reality as we know it isn't the whole story, it's just the slice the foam lets us see. Behind the curtain of classical physics, the quantum world still teems with unrealized possibilities, flickering in and out of existence too fast for even light to catch. What we call observation might just be the universe's way of taking a snapshot, freezing the foam's chaos into moments we can comprehend, one collapse at a time. Dark matter is the universe's most frustrating enigma, an invisible something whose gravity holds galaxies together, yet refuses to interact with light or matter in any way we can directly detect. For decades, scientists have chased candidates like WIMP, weakly interacting massive particles or actions. But what if the answer isn't a particle at all? Theory 14 takes us down a radical path. Dark matter might be woven into the quantum foam itself, a hidden structure lurking in spacetime's turbulent depths. Think of the foam not just as empty space's fizz, but as a cosmic iceberg, with most of its mass hidden beneath the surface. Just as ocean waves hide unseen currents, the foam's fluctuations could carry gravitational weight without ever appearing in traditional terms. Some models suggest these frothy regions might concentrate into exotic knots or filaments, distorting spacetime just enough to explain why galaxies rotate faster than visible matter alone should allow. It's like tightening an invisible rubber sheet under a spinning plate. The plate holds together, but you can't see what's pulling it taut. The math behind this idea is both elegant and thorny. Quantum foam's energy density, when averaged across the universe, might align with dark matter's observed distribution. Certain theories, like those involving gravastars or topological defects in spacetime, propose that foam-like structures could clump in halos around galaxies, their cumulative gravity mimicking the effects of traditional dark matter. The kicker: these structures wouldn't need to be made of particles. They'd be wrinkles in spacetime itself, permanently frozen into the universe's fabric during its earliest moments. Critics argue this sounds like replacing one mystery with another. After all, how do you observe something that's fundamentally part of space's architecture? But supporters counter that the foam's influence might already be visible in subtle anomalies. Take the Bullet Cluster, where two galaxies collided, and their visible gas slowed while their gravitational lensing effect attributed to dark matter kept racing ahead. If dark matter were foam-based, this could mean the collision stripped away ordinary matter while leaving spacetime's underlying structure intact, like wind scattering leaves but not the ground beneath them. The real test lies in future experiments. If dark matter stems from quantum foam, it wouldn't just bend light passing through it, it might subtly alter the speed of that light in ways particle-based dark matter wouldn't. Ultra-precise gravity wave detectors or quantum entanglement experiments could hunt for these spacetime distortions, teasing apart whether the universe's missing mass is stuff or structure. And here's the kicker: if quantum foam is dark matter, it would solve two puzzles at once. Not only would it explain dark matter's gravitational grip, but it'd also resolve the "why so ghostly" problem. Ordinary matter interacts via electromagnetism. Foam-based dark matter wouldn't need to. It's not ignoring light. It's made of the same fabric light travels through, invisible by its very nature. This isn't just about filling a gap in our equations. If proven, it would mean dark matter isn't an outsider in the cosmos. It's the universe's foundation, the hidden scaffolding holding up everything we see. And that changes not just what we know about galaxies, but what we know about reality itself. The Big Bang is often pictured as the ultimate beginning, a fiery explosion birthing space and time from nothingness. But what if that moment wasn't the true start? Theory 15 takes us to the edge of known physics, where quantum foam might not just predate the Big Bang, but could have triggered it. Imagine the universe not as a single creation event, but as a bubble rising from an eternal, frothing sea of spacetime, part of an endless cycle where universes are born, expand, and collapse like waves on a shore. At the heart of this idea lies inflation, the theory that the early universe underwent a period of exponential expansion, smoothing out irregularities and setting the stage for galaxies to form. But what sparked inflation itself? Some physicists propose that quantum foam's turbulence could have been the match that lit the cosmic fuse. In this view, the pre-Big Bang universe wasn't empty. It was a seething quantum vacuum, where fluctuations in the foam occasionally grew large enough to pinch off into self-contained universes. Ours might just be one of many, a bubble in an infinite cosmic froth. Cyclic models take this further, suggesting that the Big Bang wasn't a beginning but a rebound. Picture a universe collapsing under its own gravity, reaching a point of near-infinite density, but instead of vanishing into a singularity, the foam's chaotic energy halts the collapse, bouncing back into expansion. This isn't science fiction. The math shows that quantum effects could prevent total collapse, turning the end of one universe into the birth of another. In this scenario, the foam isn't just a byproduct of spacetime, it's the engine of eternity, eternally recycling existence. Clues might lie in the cosmic microwave background, the afterglow of the Big Bang. Certain anomalies, unexplained cold spots or swirling patterns, could be echoes of a pre-bang universe, imprints left by collisions with other bubbles in the foam. Others hunt for gravitational waves from inflation, subtle ripples that might encode the foam's structure at the dawn of time. The search is daunting, but if successful, it would rewrite cosmic history, proving our universe is just one chapter in an infinite story. Yet the deepest question remains: if the foam predates the Big Bang, does before even have meaning? Time as we know it might be a local phenomenon, a thread woven in our bubble but irrelevant outside it. The foam could be timeless, a canvas where universes flicker like fireflies, here, then gone, then here again, in a dance beyond beginnings or endings. And that changes everything we thought we knew about existence. Picture the universe as a vast, intricate tapestry, but one woven with tiny imperfections, threads ever so slightly out of place. These might not be mistakes, though. They could be cosmic scars left behind by the quantum foam's turbulent birth, frozen into the fabric of reality. This is Theory 16, where we explore topological defects, strange, stable structures like cosmic strings, domain walls, or monopoles that might have formed as the universe cooled from its fiery infancy, their shapes locked in by the foam's frenzied fluctuations. Think of it like ice crystallizing on a pond. When water freezes, the molecules arrange themselves into a rigid lattice, but sometimes flaws emerge where the patterns don't quite align. Now scale that up to the birth of spacetime itself. As the universe expanded and cooled, the quantum foam's chaotic energy might have frozen in places, leaving behind defects where spacetime's structure kinks or twists. These wouldn't be mere wrinkles, they'd be fundamental distortions, like knots in a rope that can't be undone without cutting it. Cosmic strings are the most dramatic example. These hypothetical filaments, thinner than a proton but stretching across galaxies, would carry unimaginable density. A single inch might weigh as much as a mountain. If they exist, their gravity could warp light around them, creating double images of distant stars or leaving faint, linear bruises in the cosmic microwave background. Some theories even suggest these strings might vibrate like guitar strings, emitting low-frequency gravitational waves that future detectors could catch. Then there are domain walls, immense, sheet-like structures where the laws of physics suddenly shift. Picture driving across a state line and finding the speed of light is slightly faster on the other side. These walls would separate regions of spacetime with different quantum phases, relics of a time when the foam's energy settled unevenly across the cosmos. The scariest possibility, a wall sweeping through our galaxy, could rewrite reality in its wake, altering constants like particle masses or the strength of gravity before we'd even have time to blink. But why does this matter? Because topological defects could be hiding in plain sight, shaping the universe in ways we're only beginning to grasp. The large-scale structure of the cosmos, the vast cosmic web of galaxies and voids, might owe its form to these defects' gravitational pull, like invisible scaffolding guiding where stars cluster. Even dark energy's mysterious repulsive force could stem from defects slowly unraveling, releasing pent-up energy from the foam's primordial chaos. Here's the twist: some defects might not be ancient relics. Quantum foam's turbulence could still be spawning new ones today. In particle accelerators, where energies approach those of the early universe, microscopic defects might flicker into existence for a split second before vanishing, ghostly echoes of spacetime's restless nature. If we could capture one, it'd be like finding a fossil from the universe's first moments, preserved in the wild currents of the quantum sea. The hunt for these defects is already underway. Astronomers scour the skies for strange gravitational lensing patterns or unexplained temperature variations in the cosmic background. Others analyze quantum fluctuations in lab-grown crystals, simulating how defects might emerge in spacetime structure. It's painstaking work, but the payoff would be staggering proof that the universe isn't just threaded with gravity and matter, but with the frozen fingerprints of quantum foam itself. Whether cosmic strings, domain walls, or something stranger, topological defects remind us that perfection might be overrated. The universe's most enduring features could be its flaws, knots in the tapestry, whispering secrets about the chaos from which everything arose. Light doesn't travel through the universe in a straight line, not really. Theory 17 pulls back the curtain on one of quantum foam's most subtle yet far-reaching effects: its ability to bend, delay, or even blur the very light we use to map the cosmos. Imagine the fabric of spacetime isn't a smooth highway for photons, but a bumpy backroad riddled with microscopic potholes. Every time light crosses one of these quantum bubbles, its path trembles ever so slightly, like a car's wheels jolting over gravel. Over billions of light years, those tiny deflections could add up, warping our view of the universe in ways we're only beginning to detect. This isn't just theory, it's a puzzle astronomers grapple with daily. When telescopes capture light from quasars or gamma-ray bursts at the edge of the observable universe, they sometimes arrive with puzzling variations in energy. Some high-energy photons lag behind their lower-energy counterparts by minutes or even hours, despite leaving their source simultaneously. Traditional explanations point to interstellar dust or magnetic fields, but quantum foam offers a radical alternative. Spacetime's granularity might treat different wavelengths unevenly, scattering them like prisms at the smallest scales. It's as if the universe itself has a built-in filter, subtly tinting the light that passes through it. The implications are staggering. If the foam alters light's speed based on its energy, our entire cosmic distance ladder, the toolkit astronomers used to measure the universe, might need recalibration. Galaxies we thought were 10 billion light-years away could be slightly closer or farther, their light distorted by foam we can't directly see, even more mind-bending. The foam's turbulence might impose a fundamental limit on telescope resolution, no matter how advanced our instruments become. No lens, no mirror, no detector could ever pierce below a certain scale, because spacetime itself would be pixelated, smearing out details like a camera trying to photograph fog. Experiments are already hunting for these effects. Some analyze gamma-ray bursts for telltale delays between high and low-energy photons, while others probe the polarization of light from distant pulsars for signs of quantum-scale twisting. The most tantalizing data comes from ultra-high-energy cosmic rays, particles so powerful they shouldn't survive their journey to Earth, yet they do, possibly because the foam's structure opens fleeting shortcuts through spacetime, bending the rules just enough to let them through. But the real breakthrough might come from an unexpected direction: quantum entanglement. If entangled photons sent through space show correlations that defy classical physics, their deviations could map the foam's hidden topography, like sonar pinging the ocean floor. Future satellite missions, like the proposed Quest experiment, aim to do exactly this, using the universe's most fragile quantum states as probes to chart the turbulence we've never seen. What's at stake isn't just sharper telescopes or better distance measurements. If light's journey is truly shaped by quantum foam, then every image we've ever taken of the cosmos, every swirling galaxy, every newborn star isn't a perfect snapshot. It's a portrait filtered through the froth of spacetime, a universe interpreted through static. And that means the truth might be even stranger, even wilder than the stars we think we see. Why does the quantum foam exist with precisely the properties it has? Not too turbulent to rip atoms apart, not too smooth to prevent complexity from emerging. This is where Theory 18 takes us into profound philosophical territory, connecting the foam's chaotic dance to one of cosmology's most contentious ideas, the anthropic principle. At its core, this principle suggests that the universe's fundamental constants, the strength of gravity, the mass of electrons, even the foam's own turbulence, aren't arbitrary. They're necessary, fine-tuned to allow observers like us to exist and ponder them. It's not just that we're adapted to the universe in some sense is adapted to us. Consider gravity's delicate balance. If the quantum foam's fluctuations were even slightly stronger, spacetime's granularity would destabilize matter, scattering particles before they could form atoms. Too weak, and the foam's energy might never have seeded the primordial density variations that birthed galaxies. It's as if the universe threaded a needle, a perfect equilibrium between chaos and order that made life possible. Even the foam's fractal-like structure plays a role. Its self-similarity at different scales could be why physical laws hold consistently from subatomic particles to galaxy clusters, giving science a stable rulebook to decode. But here's the debate: does this fine-tuning imply purpose? Teleological interpretations argue yes, that the foam's properties point toward a universe designed for life. Proponents see echoes of intentionality in the mathematical precision that allows carbon-based chemistry or stable planetary orbits. Critics counter with the multiverse. If infinite universes bubble from the quantum foam, each with random constants, we simply inhabit one where the dice rolled in life's favor. In this view, there's no fine-tuning at all, just survivorship bias on a cosmic scale. The foam adds a twist to this debate. Its structure isn't just a static backdrop, it's dynamic, interacting with matter and energy in ways that could actively shape the conditions for life. For instance, some models suggest the foam's turbulence might have influenced early universe symmetry breaking, determining why matter dominates antimatter. Without that asymmetry, stars and the planets circling them wouldn't exist. Even consciousness, with its alleged quantum underpinnings, might rely on the foam's ability to sustain delicate superpositions long enough for neural processes to exploit them. Yet the anthropic principle's greatest strength is also its weakness. It explains everything and nothing at once. Yes, the foam's properties permit our existence, but does that mean they were meant to? Science thrives on testable predictions, and teleology skirts dangerously close to untestable metaphysics. Still, the foam offers a middle path. If future experiments detect signatures of the multiverse-like collision scars in the cosmic microwave background, it could weaken design arguments. Conversely, finding that the foam's energy cancels too precisely for randomness might revive them. The stakes transcend philosophy. If the foam's structure is fine-tuned, it could hint at deeper layers of reality where constants aren't fixed but emergent, shaped by processes we've yet to discover. Perhaps the universe isn't just hospitable to life, it's learning from it, with the foam as an active participant in a self-referential loop. Or maybe we're just lucky, a fleeting pattern in the froth, asking questions the cosmos wasn't built to answer. Either way, the quantum foam doesn't just underpin reality, it holds up a mirror, forcing us to confront what it means to exist at all. What if the universe isn't just built on quantum foam, but protected by it? Theory 19 flips everything we've discussed on its head with a revelation straight from the frontiers of theoretical physics. The foam might not be chaos to overcome, but chaos tamed, a cosmic error-correcting code, silently safeguarding reality itself. Imagine spacetime's turbulence isn't random noise, but a highly sophisticated system for storing and preserving information, like a cosmic hard drive with built-in antivirus software. This isn't just poetic speculation, it's an idea gaining traction in quantum gravity circles, and it could solve one of physics' deepest puzzles: how reality stays coherent in a sea of quantum randomness. Error correction is something we take for granted in everyday tech. When your phone sends a text, it doesn't just blast raw data into the ether. It bundles each message with redundant bits, allowing the receiver to detect and fix mistakes from signal interference. Quantum foam could be nature's version of this, but on a scale so fundamental, it's woven into the fabric of existence. Every fluctuation, every bubble in the foam might not be a glitch, it could be part of an intricate redundancy system, ensuring that information about particles, forces, even the structure of spacetime itself isn't lost to quantum noise. Take black holes again. If the foam at their horizons encodes infalling matter's data, as we've discussed, it's not just passively recording, It's actively correcting, distributing information across spacetime structure to prevent total erasure. The math behind this is as elegant as it is mind-bending. In quantum computing, error-correcting codes work by spreading a single qubit's information across multiple entangled states, so even if one part gets scrambled, the whole remains recoverable. Apply this to spacetime's foam, and you get a universe where every particle's position, spin, and energy aren't localized to a single point, but smeared across a network of quantum connections. When a fluctuation threatens to delete a bit of reality, say, a photon's path veering unpredictably, the foam's underlying code steps in, reconstructing the original information from surrounding data. It's like a cosmic game of telephone where the message stays intact no matter how garbled the intermediate steps become. This could explain why quantum mechanics appears so paradoxically resilient. Particles can exist in superpositions, get entangled across galaxies, or tunnel through barriers, yet when we measure them, they always snap back to obey consistent rules. If the foam is correcting errors in real time, it'd mean the universe isn't just allowing quantum weirdness, it's orchestrating it, ensuring coherence emerges from the chaos. Even phenomena like quantum teleportation, where particles transmit states instantaneously, might rely on this hidden redundancy, spacetime's way of repairing the signal mid-flight. But the implications stretch far beyond subatomic physics. If the foam is a code, it might also hold the key to unifying general relativity and quantum mechanics, the holy grail of modern physics. Einstein's gravity describes spacetime as smooth and continuous, while quantum mechanics insists it's granular and probabilistic. Error-correcting codes bridge this divide by treating spacetime's smoothness as an emergent property, a collective illusion created by countless local corrections in the foam's structure. Picture a mosaic up close. It's just colored tiles, but step back and a seamless image emerges. The universe's image of smooth spacetime could be the foam's masterpiece, painted stroke by quantum stroke. Critics argue this risks being a theory of everything and nothing, an explanation so flexible it can't be disproven. Yet experimentalists are already designing tests. Some propose analyzing the holographic principle's math for error-correcting signatures, while others simulate foam-like networks in quantum computers to see if they naturally suppress noise. The most tantalizing clue might come from black hole mergers. If spacetime is a code, the gravitational waves they emit should carry subtle fingerprints of the foam's error correction at work, like glitches in a cosmic transmission revealing the encryption beneath. Whether proven or not, this theory forces a profound shift in perspective. The quantum foam isn't just the universe's foundation, it's its immune system, tirelessly debugging reality to keep the cosmos from crashing. And that means every law of physics, every star in the sky, even the thoughts in your mind right now, might be riding the edge of chaos and order, sustained by a code written in the fabric of existence itself. Quantum entanglement is the universe's ultimate magic trick, particles separated by galaxies influencing each other instantly, as if space and time don't exist. Einstein famously called it spooky action at a distance, but what if the spookiness isn't action at all? What if entangled particles aren't communicating across space but are already connected, their bond woven into the quantum foam itself? This is Theory 20, where we dive into one of physics' most tantalizing possibilities. That entanglement isn't a signal flying faster than light, but a hidden handshake happening in the foam's chaotic depths. Picture two entangled electrons, measure one's spin, and the other instantly mirrors it, no matter how far apart they are. Classical physics says this is impossible. Information can't travel faster than light. But if spacetime is foamy at its core, entanglement might not need to travel at all. Imagine the foam as a vast, invisible network, with every particle tethered to others through threads of fluctuating energy. When particles become entangled, they're not sending messages, they're tapping into this pre-existing lattice, like phones connecting through a cellular network we can't see. The foam wouldn't carry signals, it would be the signal, its fluctuations updating both particles simultaneously because they're fundamentally part of the same quantum fabric. This idea isn't just poetic, it's mathematically plausible. Some quantum gravity models suggest that entanglement could arise from wormhole-like structures in the foam, microscopic bridges stitching particles together across spacetime. These wouldn't be tunnels in the traditional sense, but shortcuts through the foam's geometry, where distance is an illusion. It's like two ants on a crumpled piece of paper. While the flat sheet makes them seem far apart, a fold could bring them nose to nose without either ant moving. In this view, entanglement isn't magic. It's topology, the hidden folds in spacetime's fabric making a mockery of classical separation. Here's where it gets even wilder. If entanglement is mediated by the foam, it might explain why quantum connections seem to ignore time. Experiments have shown that measuring one particle can affect its partner's state retroactively, as if the future reaches backward to rewrite the past. The foam's turbulent structure could allow these time-defying links, with fluctuations that don't respect cause and effect as we know them. Think of it like dropping two pebbles into a stormy pond. Their ripples don't just spread outward. They collide, merge, and twist in ways that make before and after meaningless. Critics argue this still feels like replacing one mystery with another, but supporters point to recent breakthroughs in holography and quantum error correction, where entanglement entropy, a measure of quantum connectedness, precisely matches the math describing spacetime's geometry. It's as if the universe is hinting that entanglement and the foam's structure are two sides of the same coin. Even black holes play into this. Their event horizons seem to maximize entanglement, suggesting spacetime's most extreme environments might be where the foam's role in linking particles becomes impossible to ignore. The most exciting part, we might not need to wait for a theory of everything to test this. Quantum computers, which rely on entanglement to perform calculations, could inadvertently map the foam's structure as they scale up. Unexplained noise or coherence patterns in these machines might reveal how the foam mediates connections, like static betraying a hidden radio channel. Other experiments, like firing entangled photons through ultrafast detectors, could catch the foam in the act, showing delays or distortions that only make sense if spacetime itself is participating in the entanglement. Whether this theory holds or not, it forces a breathtaking shift in perspective. Entanglement might not be a cosmic anomaly. It could be the universe's default state, with the quantum foam quietly ensuring everything stays in sync beneath the surface. And if that's true, then the spookiness isn't in the action. It's in realizing that what we call separate has never been separate at all. Take a deep breath. What you just inhaled wasn't just air. It was a storm. Every cubic centimeter of so-called empty space around you, even in the deepest voids between galaxies, is anything but vacant. Quantum foam reveals a truth that defies intuition. There's no such thing as true emptiness. Forget the classical idea of a vacuum as a sterile, static nothingness. Down at the Planck scale, space is a seething ocean of energy, where particles and forces erupt and vanish in a frenzied dance, borrowing energy from the universe's ledger only to repay it in fractions of a nanosecond. This isn't just theoretical, it's measurable. Laboratory experiments like the Casimir effect prove that empty space exerts real, physical pressure, as if the void itself is alive with invisible hands. The ancient philosophers who debated the nature of the void would be stunned. Aristotle insisted nature abhors a vacuum, while Democritus envisioned atoms moving through void as eternal and unchanging. Both missed the mark. Quantum foam shows that what we call emptiness is actually a roiling substrate, more like a pot of boiling water than an inert stage. Virtual particles, ghostly twins of matter and antimatter, constantly flicker into existence. their brief lives governed by Heisenberg's uncertainty principle. These aren't just mathematical abstractions, they're the reason atoms don't collapse and light doesn't unravel. The foam's energy acts as a cosmic glue, stabilizing the very fabric of reality against total dissolution. Contrast this with the classical vacuum of Newton or Maxwell, who treated empty space as a passive backdrop, an infinite chessboard where matter moved without resistance. Even Einstein's spacetime, for all its curvature, was still a smooth continuum. Quantum foam shatters that illusion. Imagine trying to paddle a canoe across what looks like a calm lake, only to find the water is actually a churning rapids at the microscopic level. That's the universe we live in, a place where nothingness is a misnomer, and the ground beneath our feet, the air we breathe, even the darkness between stars is humming with latent power. The implications ripple outward. If empty space isn't empty, then the universe's energy budget is vastly larger than we thought. The foam's zero-point energy, the residual jitter that remains even at absolute zero, could theoretically power starships or warp spacetime itself if we could tap into it. Some theories even suggest that dark energy, the mysterious force accelerating cosmic expansion, might be the foam's energy bubbling up on cosmological scales, a reminder that the universe's foundations are anything but serene. Yet here's the paradox: this bustling microcosm doesn't disrupt daily life. Your coffee stays in its cup, light travels in straight lines mostly. The foam's chaos cancels out statistically, leaving behind the smooth, predictable reality we recognize. It's like the static on an old TV up close. It's noise, but step back and the picture emerges. This equilibrium between frenzy and order isn't an accident. It's a delicate balance struck over billions of years, a testament to the universe's ability to weave stability from turbulence. So the next time you gaze at the night sky, remember, the vast black expanse isn't dead space. It's a living, breathing entity, its apparent stillness masking a quantum maelstrom. The foam doesn't just fill the gaps, it is the gaps, the hidden heartbeat of the cosmos, pulsing beneath the illusion of the void. And that changes everything. String theory has long danced on the edge of physics, a tantalizing idea that reality's fundamental building blocks aren't particles, but tiny, vibrating strings. Now imagine these strings don't just hum in empty space. They are the space, their vibrations weaving the quantum foam itself into existence. This is where Theory 22 takes us, merging two of physics' most enigmatic ideas into a breathtaking vision. That spacetime's turbulent froth might actually be the symphony of countless strings, each oscillation birthing the bubbles and fluctuations we call quantum foam. At string theory's core is a radical rewrite of dimensionality. Instead of the familiar 4 dimensions, 3 of space, 1 of time, it proposes 10 or even 11, with the extra dimensions curled up so tightly they're invisible to us. Now picture those hidden dimensions not as static loops, but as dynamic, frothy landscapes where strings stretch, twist, and collide. Every tremor in a string could manifest as a bubble in the foam, making spacetime's turbulence not random chaos, but the emergent rhythm of deeper vibrational patterns. It's like hearing static on a radio, only to realize it's actually the overlapping echoes of 1,000 orchestras playing at once. The math behind this alignment is staggeringly elegant. In string theory, different vibrational modes of a string correspond to different particles. An electron might be a string vibrating at one frequency, a quark at another. Apply this to the foam, and suddenly those virtual particles popping in and out of existence aren't just quantum ghosts. They're strings briefly flickering into higher energy states before settling back down. Even gravity finds its place here. The hypothetical graviton, long sought as gravity's quantum carrier, could be a string vibrating in just the right way to stitch spacetime's curvature into the foam's fabric. But the real magic happens when strings interact with brain's higher dimensional membranes that string theory suggests might exist. Imagine a brain fluttering like a sheet in the wind, its movements creating ripples in the surrounding foam. Some models propose our entire universe could be a three-dimensional brain floating in a higher dimensional bulk, with quantum foam as the interface where our brain's vibrations meet the bulk's hidden geometry. This could explain why gravity feels so weak compared to other forces. It might be leaking into extra dimensions through the foam, diluting its strength in our observable world. Critics argue this feels like stacking one unproven idea atop another, yet there's a compelling logic to it. The foam's Planck scale fluctuations align eerily with the tiny sizes string theory predicts for its strings around 10 to the minus 35 meters. Even the foam's energy density mirrors the colossal tension strings would need to vibrate at such scales, and when string theorists simulate high-energy collisions, the resulting spacetime distortions look suspiciously like foam-like structures emerging from the chaos. The implications could redefine reality's building blocks. If strings underpin the foam, then particles aren't just in spacetime. They are spacetime, their properties dictated by how the foam's underlying strings knot and vibrate. Dark matter might be strings oscillating in modes we can't yet detect, while dark energy could stem from brains slowly stretching the foam's structure like taffy. Even the Big Bang might resolve into a brain collision, its aftermath frozen into the foam's primordial turbulence. For now, the marriage of string theory and quantum foam remains a beautiful hypothesis. But as particle accelerators probe ever higher energies and telescopes map the universe's large-scale structure, we might one day catch the echoes of those strings, their vibrations humming in the foam's depths, rewriting the score of the cosmos. Imagine a clock that ticks forever without any energy, a structure that moves even in its lowest possible energy state, defying the usual rules of thermodynamics. This isn't science fiction, it's the bizarre world of time crystals, a phase of matter that could find its most exotic form within the quantum foam's seething depths. Theory 23 explores the possibility that spacetime's turbulence doesn't just host particles and forces. It might cradle these strange, self-sustaining structures, where time itself becomes a canvas for perpetual motion. Time crystals were once dismissed as impossible until Nobel laureate Frank Wilczek proposed their existence in 2012. Unlike conventional matter, where atoms settle into static arrangements at absolute zero, time crystals exhibit rhythmic, repeating patterns in time rather than space. Picture a diamond where the atoms not only form a lattice but also oscillate in perfect sync, forever cycling between states without energy input. Now transplant this idea into the quantum foam, where spacetime's fluctuations could act as a nonlinear medium, enabling these crystals to form spontaneously. The foam's ceaseless churn might provide the perfect environment for time crystals to emerge, like ice crystallizing in turbulent water. What makes this idea revolutionary is how it reshapes our understanding of equilibrium. Normally, systems in their ground state are motionless. Think of a pendulum at rest. But time crystals break this symmetry, introducing motion as a fundamental property rather than an excited state. In the quantum foam, this could mean bubbles of spacetime that tick like microscopic metronomes, their rhythms locked to the foam's fluctuations. These wouldn't be machines needing energy, they'd be intrinsic to spacetime's fabric, their motion woven into the universe's lowest energy configuration. Practical implications are staggering. If time crystals exist in the foam, they could serve as natural quantum memory units, preserving information in their cyclic patterns despite decoherence. Future quantum computers might exploit these structures to stabilize qubits, leveraging their innate resistance to entropy. Even more tantalizing, if time crystals can interact with gravity, their rhythmic distortions might subtly warp spacetime, creating detectable signatures in precision instruments like atomic clocks or gravitational wave detectors. Yet the deepest allure lies in the philosophical shift. Time crystals in the foam would blur the line between time and matter, suggesting that the universe's flow isn't just a backdrop, it's a participant with its own dynamics etched into the quantum froth. Every tick of these cosmic clocks would be a reminder time might not pass, it might pulse, resonating through the foam's hidden lattice, echoing the universe's heartbeat. What if the quantum foam's frenzied flickering isn't just the fabric of reality, but the glitches in its code? Theory 24 plunges us into one of the most debated ideas of our time, the simulation hypothesis, which suggests our universe might be an artificial construct, an elaborate digital projection where the foam's pixelated structure represents the underlying resolution of whatever's running the program. It's a concept that blurs the line between metaphysics and cutting-edge physics, and it all hinges on whether spacetime's turbulence looks less like natural chaos and more like the artifacts of a cosmic rendering engine. Proponents point to the foam's granularity as Exhibit A. Just as a video game breaks down into pixels when you zoom in too close, the universe's smoothness dissolves into Planck-scale fluctuations, suggesting a fundamental pixel size to reality. Even the speed of light, they argue, could be a processing limit, a cosmic frame rate preventing the simulation from overloading. The holographic principle we explored earlier fits neatly here. If our three-dimensional world is projected from a two-dimensional boundary, it mirrors how modern CGI renders complex scenes from simpler data structures. Even quantum indeterminacy particles existing in multiple states until observed could be an optimization trick, like a video game only rendering details when a player looks at them. But skeptics counter with physics' messy elegance. If we're in a simulation, why would it include pointless complexities like the weak nuclear force or the precise mass of neutrinos? Why simulate quantum foam's chaotic energy when a cleaner, more efficient design would suffice? Some argue the universe's mathematical depth, from fractals in fern leaves to the exact ratios in stellar spectra, feels organic, not engineered. And then there's the simulation paradox. If advanced civilizations commonly create simulated worlds, why aren't we drowning in nested layers of reality, each simulation spawning more until the cosmic server crashes? The debate takes a wild turn with black holes. These cosmic data shredders, as we've seen, might encode information in their event horizons, echoing how error-correcting codes protect digital data. If black holes are nature's garbage collectors, could their behavior hint at a universe managing memory constraints? On the flip side, quantum entanglement's spooky connections defy classical computing logic. Simulating trillions of entangled particles in real time would require resources exceeding the universe itself. Unless, of course, the simulation's architecture transcends our understanding of computation entirely. Ethical quagmires emerge too. If we're simulations, do our choices matter, or are we scripted characters in some higher civilization's cosmic experiment? Some theorists propose testable signatures, look for rounding errors in physical constants over time, or anomalies in high-energy particle collisions that resemble computational overflow glitches. Others suggest searching for evidence the universe runs on discrete math, like finding the cosmic equivalent of a pixel grid in the polarization of ancient starlight. Yet the most compelling counterargument might be simplicity itself. The simulation hypothesis, for all its intrigue, doesn't actually explain anything, it just pushes the mystery up one level. Who created the simulators? What physics governs their reality? At some point, you still need a real universe with rules to build the first simulation. Quantum foam, in this view, might not be proof of a programmed cosmos, just a reminder that reality, whether simulated or not, is far stranger than we ever imagined. Ultimately, the simulation debate isn't about answers. It's about questions about why the universe feels so finely tuned, whether math is discovered or invented, and if the foam's static is noise or a message. Until we crack quantum gravity's code, the pixels on reality's screen will keep flickering, leaving us to wonder, are we players, observers, or lines in someone else's cosmic script? Particles shouldn't be able to walk through walls, yet in the quantum world, they do exactly that. This bizarre phenomenon, called quantum tunneling, lets electrons and other particles bypass seemingly insurmountable energy barriers as if they've discovered hidden doorways in reality. But what if those doorways aren't just mathematical quirks? Theory 25 proposes something astonishing. That quantum tunneling might be the foam's doing, a direct result of spacetime's turbulent, flickering nature at the smallest scales. Imagine a hiker facing a mountain range. Classically, they'd need enough energy to climb over, but if the ground beneath them kept shifting, sometimes lifting them partway up the slope, sometimes creating momentary gaps in the rock, they could slip through without ever summiting. That's tunneling in the quantum foam, where spacetime's instability provides fleeting shortcuts through nature's barriers. This isn't just theoretical sleight of hand. Without tunneling, the sun wouldn't shine. Nuclear fusion relies on protons overcoming the intense electromagnetic repulsion between their positive charges, a feat impossible under classical physics. Yet in the sun's core, quantum foam's fluctuations give protons an escape hatch, allowing them to tunnel through the barrier and fuse into helium, releasing the energy that fuels life on Earth. The same process powers modern technologies like tunnel diodes in electronics, where electrons bypass circuit barriers with eerie efficiency. Even your sense of smell might depend on it. Some theories suggest odor molecules activate receptors not by direct contact, but by tunneling electrons triggering neural signals. Here's where the foam's role gets truly radical. Traditional explanations treat tunneling as a probabilistic fluke, a particle borrowing energy to leap a barrier. But foam-based models suggest spacetime's granularity reshapes the landscape itself. At the Planck scale, energy barriers aren't smooth walls. They're more like chain-link fences rattling in a storm, with gaps constantly opening and closing. Particles don't magically teleport. They exploit the foam's dynamic texture, slipping through spacetime's ever-shifting cracks. Some theories even propose that what we call tunneling is actually particles taking microscopic wormholes in the foam, transient bridges forming and vanishing too quickly to detect. The implications stretch far beyond academic curiosity. Fusion reactors, long touted as clean energy's holy grail, struggle because forcing nuclei together demands extreme temperatures. But if we could harness the foam's tunneling effects, perhaps by engineering materials that amplify spacetime's fluctuations, we might lower the energy needed for fusion, turning sci-fi power plants into reality. Quantum computers already rely on tunneling for qubit operations. Optimizing this process could unlock unprecedented processing speeds. Even medicine might benefit, with tunneling enzymes in cells offering clues for designing nanomachines that repair DNA. Yet the foam's tunneling might also hide cosmic dangers. If spacetime's structure permits too much tunneling on macroscopic scales, entire atoms could unpredictably phase through solid matter. Thankfully, decoherence usually prevents this, but in extreme environments like neutron star crusts or black hole accretion disks, who knows what strange tunneling phenomena might emerge. The foam's chaos giveth, and it may taketh away. What makes this theory so compelling is its testability. Recent experiments with ultrafast lasers have captured tunneling electrons in action, revealing delays that hint at the foam's involvement. Other researchers simulate tunneling in materials with foam-like disorder, finding eerie parallels to quantum predictions. If future labs can isolate spacetime's fluctuations from other effects, we might witness the foam's handiwork directly, a proof that the universe's walls have hidden doorways after all, and the keys are woven into spacetime's restless depths. The universe didn't just expand after the Big Bang, it exploded, ballooning from subatomic size to cosmic scales in less than a trillionth of a second. This runaway growth spurt, cosmic inflation, solved mysteries like why the universe looks so uniform in all directions. But here's the puzzle inflation left unanswered. Where did the seeds for galaxies come from? Enter quantum foam, a frothy sea of spacetime fluctuations that might have written the blueprint for everything we see today. Picture the infant universe as a blank canvas stretched impossibly thin by inflation. Perfectly smooth, it should have stayed that way, leaving behind a featureless void. Yet when we look up, we see galaxies, clusters, and vast cosmic webs. The only way this makes sense is if tiny quantum ripples, magnified by inflation's explosive stretch, became the gravitational wells where matter first pooled. Those ripples could trace back to the foam's primordial churn. At the Planck scale, spacetime isn't comets, a tempest of virtual particles and energy fluctuations. Inflation's hyper-stretching would have taken these microscopic tremors and blown them up to cosmic proportions, like amplifying the static of a vinyl record until it becomes a symphony. The math bears this out. Models matching quantum foam's predicted fluctuation spectrum align almost perfectly with the faint temperature variations we see in the cosmic microwave background, the afterglow of the Big Bang. These billionth of a degree differences aren't just noise, they're fossilized imprints of the foam's turbulence stretched into the seeds of galaxies. But here's where it gets wilder. The foam's fluctuations weren't just preserved by inflation, they might have driven it. Some theories propose that inflation wasn't a one-time event but a chain reaction, with quantum bubbles in the foam nucleating new inflationary domains like soap suds splitting in a sink. Each bubble could become its own universe with slightly different physics, while ours merely happens to have the right conditions for stars, planets, and life. This would mean the cosmic web we call home isn't just shaped by the foam, it's a direct descendant, its structure echoing quantum randomness frozen into spacetime's bones. Critics argue this paints too neat a picture. If quantum foam seeded all structure, why do galaxies cluster in ways that occasionally defy predictions? Some anomalies, like the mysterious cold spot in the cosmic microwave background, might hint at pre-inflation physics we don't yet grasp, or even collisions with other inflationary bubbles in a multiverse. Others suggest the foam's role wasn't passive but interactive, with fluctuations feeding back into inflation's energy field like gusts stoking a fire. The stakes couldn't be higher. If the foam's fingerprints are indeed etched into the universe's large-scale structure, decoding them could reveal inflation's energy scale, the nature of dark matter, even the shape of higher dimensions. Future telescopes, like the European Space Agency's Euclid or NASA Spherex, will map billions of galaxies to test these ideas, hunting for statistical patterns that trace back to the foam's quantum origins. What's breathtaking isn't just the science, it's the cosmic irony. The same turbulence that makes empty space seethe with particles also penned the recipe for galaxies. The foam's chaos didn't just survive the Big Bang, it became the universe's architecture, turning quantum static into celestial cathedrals. And that means every star, every planet, every atom in your body might owe its existence to spacetime's oldest dance, a dance that began before time itself. We've grown up thinking of space as having three dimensions: length, width, and height, with time as the fourth. But what if the quantum foam isn't just frothing within these familiar bounds? What if its turbulence is actually the spillover from dimensions we can't see, folded so tightly they're hidden in plain sight? This is the spine-tingling premise of Theory 27, that the foam's ceaseless churn might be our best clue to extra dimensions, realms beyond perception predicted by Kaluza-Klein theory and M-theory. Picture a garden hose stretched across a field. From a distance, it looks like a simple one-dimensional line, but zoom in, and you'll find its surface curves into a second dimension, one that was always there, just too small to notice. Now imagine that hose is space-time, and the extra dimension isn't just a cylindrical wrap but a complex landscape with 7 or more hidden directions. The quantum foam's fluctuations could be the echoes of particles or forces moving through these folded dimensions, like ripples betraying the shape of a pond's depths. Here's how this might work. In Kaluza-Klein's vision, electromagnetism and gravity unite elegantly if we posit a tiny, curled-up fifth dimension. The foam's energy could be where this dimension leaks into our reality, its vibrations manifesting as virtual particles or even dark matter. M-theory takes this further, suggesting 11 dimensions where strings and brains interact, with the foam acting as the interface. Those fleeting wormholes and quantum bubbles we've discussed. They might not just tunnel through our universe, they could pierce into these higher dimensional spaces, ferrying energy or information along unseen pathways. The smoking gun could lie in gravity's puzzling weakness. While electromagnetism binds atoms and the strong force holds nuclei together, gravity is absurdly faint by comparison. If it's leaking into extra dimensions through the foam, that would explain its apparent dilution in our 3D world. Particle colliders like the LHC have hunted for signs of this tiny missing energy in collisions that might have slipped into hidden dimensions. So far, no luck, but the foam offers another angle. If extra dimensions exist, their geometry should leave statistical fingerprints in spacetime's fluctuations. Cosmology provides tantalizing hints. The universe's startlingly uniform temperature, a puzzle known as the horizon problem, could make sense if higher dimensions allowed rapid shortcuts in the early cosmos. Even dark energy's repulsive force might stem from brains' higher dimensional objects pushing against our universe through the foam's medium. Some models suggest that what we perceive as vacuum energy is just the gravitational shadow of neighboring dimensions pressing in, like a hand dimpling a rubber sheet from below. The wildest implication: if extra dimensions are tucked into the foam, they might not be static. They could vibrate, resonate, or even evolve, subtly altering the laws of physics over cosmic time. Constants like the speed of light or the fine structure ratio might drift as the foam's hidden geometry shifts. There's even speculation that consciousness itself, with its mysterious quantum hints, could be tapping into these dimensions, processing information in spaces our brains aren't built to perceive directly. Detecting this would require rewriting our experimental playbook. Gravity wave observatories might catch anomalous frequencies, high-dimensional overtones in the spacetime, ripples from colliding black holes. Quantum entanglement experiments could reveal correlations that only make sense if particles are communicating through extra-dimensional links. Or we might find anomalies in the cosmic microwave background, like repeating patterns hinting at a universe folded into higher dimensional shapes. Yet skeptics urge caution. Extra dimensions remain mathematically elegant but observationally elusive. The foam's turbulence could just as easily stem from quantum field theories' known quirks without invoking new dimensions. And if these realms are compacted smaller than a quadrillionth of a proton's width, as some theories suggest, they might be forever beyond our reach. But here's the beauty of this idea: the quantum foam doesn't just challenge what we know, it redefines what's possible. If extra dimensions are real, then every law of physics, every force we take as fundamental, might be the 3D shadow of something vaster. The foam's ceaseless dance could be the closest we'll ever get to glimpsing the universe's full dimensionality, not as a static stage, but as a living, breathing, multidimensional tapestry whose threads flicker just beyond our sight. Gravity has always been the rebel of the fundamental forces, stubbornly refusing to fit into the neat framework that binds electromagnetism and the nuclear forces together. While the other three play by the rules of quantum mechanics, gravity dances to Einstein's tune of curved spacetime, leaving physicists scratching their heads for nearly a century. But what if the quantum foam isn't just background noise? What if it's the missing puzzle piece, the common ground where all four forces finally shake hands? This is Theory 28, where we explore the radical idea that spacetime's turbulent froth might be the key to unification, the secret bridge between gravity and the quantum world. Let's rewind for a moment. The standard model of particle physics is a triumph. explaining how electromagnetism and the strong and weak nuclear forces govern everything from atomic bonds to supernova. But gravity, it's the loner described perfectly by general relativity on cosmic scales, but crumbling when we zoom into the quantum realm. The problem isn't just academic. Without a unified theory, we can't fully understand black holes, the Big Bang, or even why the universe is put together the way it is. Quantum foam offers a tantalizing solution. Spacetime's frenzied fluctuations might blur the lines between forces, creating an environment where gravity's smooth curves emerge from the same chaotic substrate as quantum fields. Picture the foam as a stormy sea where particles aren't just moving through space, they're part of space, their behavior shaped by the foam's churn. In this view, gravity isn't a separate force bending spacetime from the outside. It's the collective effect of countless quantum interactions in the foam, like the way a crowd's roar emerges from individual voices. String theory hints at this, suggesting that gravitons, the hypothetical carriers of gravity, might be vibrations of spacetime's underlying strings, with the foam acting as the medium through which they ripple. Even loop quantum gravity, a rival approach, describes spacetime as a network of interconnected loops, where gravity's strength depends on how tightly those loops knot and twist in the foam. The implications are staggering. If the foam unifies forces, it could explain why gravity is so weak compared to electromagnetism. Imagine the other forces as concentrated beams of energy, channeled through the foam's structure, while gravity spills across dimensions, diluted by the foam's extra-dimensional leaks. This might also solve the infamous hierarchy problem, the puzzling gap between gravity's feebleness and the other force's potency. The foam's turbulence could be the great equalizer, smoothing out these disparities in ways we're only beginning to model. But unification isn't just about gravity. The foam's dynamics might also explain the mysterious behavior of the strong force which binds quarks inside protons. At extremely high energies like those in the early universe, the strong force weakens, a phenomenon called asymptotic freedom. Could this be due to the foam's fluctuations, freeing quarks by temporarily altering spacetime's texture? Similarly, the weak force's handedness, its preference for interacting with left-handed particles, might stem from asymmetries in the foam's structure, like a cosmic screw threading reality at the tiniest scales. Critics argue this is a stretch. After all, we've yet to detect direct evidence of the foam's role in force unification, but supporters point to tantalizing clues. Certain quantum gravity models predict that at Planck-scale energies, the distinctions between forces melt away, their strengths converging as if drawn toward a single origin point. Even the Higgs field, which gives particles mass, might owe its properties to interactions with the foam's energy density, like a ship finding stability amid turbulent waves. The real test lies in experiments that probe spacetime's granularity. Future colliders aiming for higher energies might spot deviations in particle behavior that hint at the foam's influence. Gravity wave detectors, tuned to ever finer frequencies, could catch echoes of unified forces in the ripples from black hole mergers. And if we're very lucky, the foam's fingerprints might even appear in high-energy cosmic rays particles that carry energies so extreme, they briefly recreate conditions where all forces were one. What's thrilling isn't just the science, it's the philosophical shift. If the foam truly unifies forces, then the universe isn't built on separate laws but on a single, breathtaking symmetry, fractured into diversity by the cooling of the cosmos. Gravity isn't an outsider, it's a quantum force in disguise waiting for us to decode its hidden language. And every tremor in the foam, every fleeting bubble of energy, could be a whisper from that deeper unity, a reminder that reality, for all its complexity, might be simpler than we ever dreamed. Quantum computers don't just calculate, they reshape reality to find answers. While classical computers plod through problems step by step, their quantum counterparts exploit superposition and entanglement to explore countless solutions at once. But here's the mind-bending twist. What if this quantum advantage isn't just a quirk of engineering, but a reflection of the universe's deepest nature? Theory 29 pulls back the curtain on a stunning possibility that quantum foam isn't just a backdrop for computation, but the reason quantum computers outperform classical ones. Spacetime's turbulent froth might be the ultimate co-processor, giving quantum systems a natural edge by mirroring the universe's own chaotic creativity. Think of a quantum computer as a surfer riding the foam's waves. Classical bits are like swimmers fighting the current. Each stroke is deliberate, each movement linear. But qubits, the quantum equivalent of bits, don't fight the turbulence, they harness it. Superposition lets them exist in multiple states simultaneously, while entanglement links them across space, allowing them to sample solutions in parallel. This isn't just clever design, it's physics echoing physics. The quantum foam's ceaseless fluctuations provide a natural environment for this parallel processing, where uncertainty isn't noise, it's fuel. Consider how error correction works in quantum systems. Classical computers rely on redundancy, copying bits to preserve data, but qubits can't be copied due to the no-cloning theorem, so engineers use topological tricks, distributing information across entangled states. Strikingly, this mirrors how the foam preserves information at black hole horizons, encoding data in spacetime's structure rather than traditional matter. It's as if nature has been running error-corrected quantum computations for billions of years with the foam as its hardware. Now imagine scaling this up. A fully realized quantum computer wouldn't just solve problems faster, it would reframe them. Factorization, optimization, even protein folding could become trivial, not because the computer is smarter, but because it's leveraging the universe's native language, quantum foam's probabilistic churn. Even more tantalizing, certain problems might be unsolvable classically, not because they're complex, but because their solutions exist in the foam's geometry, accessible only to systems that speak spacetime's dialect. Yet the foam's role might cut both ways. Decoherence, the bane of quantum computing, could be spacetime's turbulence interrupting calculations, like static disrupting a radio signal. Some researchers speculate that mastering decoherence might require listening to the foam's rhythms, synchronizing qubits with Planck scale fluctuations. Future quantum chips might need foam-inspired architectures, with qubits arranged to mimic spacetime's fractal patterns or shielded using principles borrowed from black hole thermodynamics. The stakes: a quantum internet could emerge, with entanglement distributed through the foam's hidden networks. Cryptography would need overhauling, as foam-aware algorithms crack classical codes effortlessly. Even AI might leap forward, with neural networks trained not on data, but on quantum foam's emergent patterns, learning, in effect, from the universe's own playbook. But here's the humbling truth: we may be the ones playing catch-up. The universe has been performing quantum computations since the first stars ignited. It's spacetime froth optimizing galaxy formation, particle interactions, even life's molecular dances. Quantum supremacy isn't just a milestone, it's us finally tapping into nature's operating system, where the foam isn't our obstacle but the ultimate teacher. What happens to the quantum foam when the universe itself is breathing its last? Theory 30 takes us to the edge of eternity, where spacetime's restless churn must finally confront the cosmos' ultimate fate. Whether the universe ends in fiery collapse, icy stillness, or something stranger, the foam's destiny could rewrite the very definition of the end. Picture a cosmos where stars have burned out, black holes have evaporated, and galaxies are scattered dust, yet beneath it all, the foam still flickers. Is it the last heartbeat of reality or the seed of something new? In a heat-death scenario where entropy maxes out and the universe becomes a featureless void, you'd expect the quantum foam to settle into silence. But here's the twist: even at absolute zero, the foam's zero-point energy ensures it never fully sleeps. Virtual particles will still wink in and out of existence. Space-time will keep bubbling at the Planck scale, just with no structures left to notice. Some models suggest this endless fizz could eventually nucleate a new Big Bang, like a single spark reigniting a dead fire. The foam's fluctuations might not just outlast the universe, they could reboot it, turning heat death into a cosmic pause rather than a full stop. Then there's the Big Crunch, a fiery finale where gravity triumphs, pulling everything back into a singularity. As space-time itself contracts, the foam's bubbles would be squeezed tighter, their energy density skyrocketing. But instead of vanishing, they might reach a critical point where quantum pressure halts the collapse, triggering a bounce. Picture a rubber band stretched to its limit, then snapping back with enough force to launch a new expansion. The foam wouldn't die, it'd rebound, recycling the universe's ashes into a fresh beginning. But the wildest possibility, the foam's turbulence isn't just resilient, it's evolving. In a cyclic cosmos, each iteration might tweak the foam's structure, fine-tuning constants like gravity or the speed of light over endless cycles. Our universe's laws could be the latest draft in an infinite series, with the foam as the editor, rewriting the rules each time. Or perhaps the foam is slowly freezing, its fluctuations damping over eons until spacetime becomes smooth and static, a cosmic ice age where even quantum noise fades to silence. The truth is, we don't know, but the fact that we can ask, that the foam's fate is even debatable, shows how far physics has come. Once, the universe's end seemed simple, fire or ice. Now, thanks to the quantum foam, it's a doorway not just to endings, but to beginnings we can't yet imagine, and that changes everything. From the idea that quantum foam could be stitching reality together like invisible threads to the wild possibility that it's running the universe like a cosmic supercomputer, we've journeyed through 30 mind-bending theories that turn spacetime's turbulence into a portal for rewriting physics itself. Each one peels back another layer of the ordinary, revealing a universe far stranger than we ever imagined. Whether it's black holes encoding information in their foam-laced horizons, or dark energy bubbling up from spacetime's restless churn, these theories don't just challenge what we know, they shatter the very framework we use to understand existence. Think about it, the chair you're sitting on, the stars above you, even the passage of time might all be emergent illusions, flickering into being atop a quantum storm we can't yet see. Some theories paint the foam as a frenzied artist sculpting particles from chaos. Others see it as a meticulous archivist preserving every bit of cosmic history in spacetime's wrinkles. And then there are the ideas that push beyond our universe entirely, wormholes threading the foam to other dimensions, or multiverses sprouting like bubbles in an infinite froth. The sheer diversity of these visions proves one thing: quantum foam isn't just a curiosity, it's the frontier where our boldest questions collide. But here's the thrilling part, we're not just passive observers. Every experiment probing spacetime's graininess, every telescope hunting anomalies in the cosmic microwave background, even every qubit in a quantum computer is a step toward testing these ideas. Some will fade into the archives of beautiful but wrong hypotheses. Others might crack open reality's code, revealing secrets about dark matter, the Big Bang, or forces we've yet to name. And the most humbling thought, today's wildest theory could be tomorrow's textbook fact. After all, black holes and gravitational waves once sounded like science fiction too. So stay curious, wonder about the foam's hum in the quietest corners of space, its whisper in the bonds between atoms, its fingerprints on the edge of a black hole's shadow. The greatest discoveries often start with a simple question. What if the universe is a hologram? What if time is an illusion stitched together by quantum static? What if we're standing at the brink of answers that will rewrite not just physics, but what it means to exist at all? The quantum foam doesn't just hold those secrets, it is the secret. And the adventure to unravel it has only just begun.